psi naught h naught psi naught. Now this is very important. We now have an expansion for E1, and we can even go further for E2. In fact, if we extend perturbation theory a little more, we can get an expansion for psi1 and psi2. We can technically continue infinitely, but these terms are not as useful and just make attempting to extract a solution worse. So, as a last example, let's see what happens when we take the infamous infinite square well which has the well-known solution to one of the only things that we were able to solve analytically. U is equal, psi is equal to sine squared x. Well, if you normalize it, it's going to be the square root of 2 over a sine squared x. If we take this, and now, let's say we make a little perturbation, we raise the potential by a small amount. Since this is such a simple perturbation, I mean, it's constant, for goodness sake. The perturbation lambda h prime could basically be written as lambda if we wanted it to. We're just adding a constant to the entire potential function. If we have that now, what's probably not very surprising to you is that E1, the energy level we get is what? Well, it was psi naught, it should be psi naught h prime psi naught. This is equal to what? Well, consider that, h prime, E1 here is just E naught plus the magnitude of the perturbation, which is kind of strange, but it makes sense that a first order approximation is giving exact results for the potential when it's such a constant perturbation. Now, if it is not a constant perturbation, something like this, then you get that E1 is equal to E naught plus V naught over 2, which is not the exact formula, but